Okay, time is 12:30. Let's get started here. So assignment number 5 has been passed back since our last class. Are there any questions about it? Okay, assignment number 6, we will talk about that at 1:20 today. It is due Wednesday, November 30th at noon. Are there any questions before we get going here? Okay, so we're on page 14 talking about graphics. And so what we're going to be doing now is talking about some useful single variable summary plots like histograms, box plots, and dot plots. And the plots themselves are not difficult, just you may not necessarily have seen exactly how to do these before. And so we're going to begin with a histogram, and we're going to continue working with GPA data for this histogram. And simply, if I look at the high school GPA, I can use the Hist function where the X argument says, well, what do you want to plot? So I'm going to say GPA $HS.GPA. So GPA is a data frame, and HS.GPA is one variable in that data frame. Put a nice little X-axis label, put a nice title to the plot, and when I execute that code, I get my nice histogram right there. R automatically chooses a particular number of classes for the histogram by just executing the code that I did here. Now, in the notes, I show you, well, what happens if you want to actually specify a certain number of classes or the actual classes themselves. And that's not too difficult. You can use the breaks argument with Hist to specify I want my first category to be between 0 and 0.5. The next category, 0.5 to 1, and so on. And so when I execute that code, then we can see that indeed that's what was chosen. Notice also how that allows me to expand the x-axis limits. You could also use the xlim argument that we saw in plot to do the same thing in terms of the x-axis limits itself. Another useful argument in Hist is n class. Let's verify that is correct. Yes, on page 15. One could say, let me get back to my program. One could say n class equal, for some reason I wanted 10 categories. That would make sense when you have a sample size of 20, but I could still do that. And this is what we get for our plot. And you can see how the bars are smaller in width. Okay. Now, in the notes, I actually show, well, what if you were to do some comparisons between the high school and college GPAs? You might want to compare the different distributions themselves. And what you could do is simply do 2 histograms. And to do a better comparison, what you could do is put one histogram for high school GPA on the top and one for college GPA on the bottom. Make sure your classes for that histogram are exactly the same so you can make direct comparisons. And to do this 2 plots on one graphic sheet, I'm going to use the par function, which we've seen many times before. I believe, at least in the notes, I believe we also talked about in class the MF row argument, which stands for make frame by row. I want 2 rows and 1 column for my graphics window. And then when I do that, then I get exactly what I mentioned, that we have this nice little comparison of the 2 histograms. Now, after seeing this and planning for this in class, I was thinking, probably would have been also good to make the y-axes exactly the same. How do you think I could do that? In terms of the height of that y-axis. What would be the argument, do you think? Same as in plot. Yeah, use ylim equals c parentheses 0 comma maybe 8 in parentheses. So that means you might have to run this more than once to see, well, what's the maximum there. And there are fancier ways that you could do this too, such as This is actually be demonstrated a little bit later, but we can do this now. Suppose I do something like this. I create an object called max.y, gets, then I use the max function. And inside this max function, I put both the high school and college GPAs, like that. So if I execute that code, actually no, I apologize, that will not work. Excuse me. In the end, it actually will be a little bit more complicated. I'll post it to the listener because it's going to take me a few minutes to actually do it in class. I don't want to take the time. Excuse me. But one way is that you could do the two plots and simply look at the plots to get an idea, well, what should that max for that y-axis be? Okay. Excuse me. Okay, so let me go to the notes here. Talk about that. Well, let's say that you want to also put a normal distribution approximation on these histograms. It's a common thing that one would do. You could do it with other distributions as well. We're just going to talk about the normal distribution here because the syntax is essentially the same. Now, in this particular setting, to plot then the normal distribution on top of it, I need to rescale the y-axis. Because let's take a look at the y-axis on these histograms. Notice how they are counts in terms of, oh, give me my red pen back, in terms of 0 to all the way up to 8. And I want to plot essentially f of x, the density function itself. And so because of that, I need to make that y-axis be the same scale as what the density function would be. And so you might be thinking, okay, well, all you need to do is take, let's say now, the frequency for a particular class divided by, let's say, the sample size. We'll just call it n. You could do that, but it won't necessarily work in all cases because you also have to account for the class width. And so you need to actually do class width here. So in this case, it would be 0.5. And what that's going to do is if you rescale the height of all those bars using this nice little expression there, that's going to put it on exactly the same scale as what the normal density or any kind of density function would need. Try it on your own with or without that class width there just to see that indeed that is true. And so then to tell R that you want that rescaling, you use the argument in Hist freq for FREQ, and the default was true, meaning you put the frequencies of each classes. You need to change it to false. And now the y-axis will be rescaled so you can plot any kind of density function on it. To plot the density function itself, use curve. We've seen this before, where my expression is density norm. That's my function for normal density that we've seen before. Remember how curve operates using an x argument. And then, well, what do I want for the mean? What do I want for the standard deviation then for this normal distribution? Well, if I want to find the best fitting normal distribution to this data, what do I use? Well, the mean and standard deviation from the data itself. So I say for the mean argument, the mean of all the high school GPAs. For the SD or standard deviation argument, I want the standard deviation of all the high school GPAs. We'll make it a red curve on it, and then we need to add it to the current plot. So add equal true. I do the same thing for the college GPAs as well, and here are my two plots. What do you think about normality here? It's really hard to make a judgment when you only have a sample size of 20. Okay? you want to try this on your own, try simulating some data from a normal distribution of size 20 and do exactly the same plot. Some of the plots will say, yeah, that looks kind of normal. Other plots will not. But you know that indeed you really do have a normal distribution. That just shows you how difficult it is when you have a small sample size such as this to make a normal distribution assumption, a normal distribution judgment. At least, it's mound shape. Not quite as much symmetric as what you would like, but you can't really say, oh, there's strong evidence against normality here. Even this right here, not too bad. I mean, you're probably concerned about that, but again, small sample size. Okay, let's talk about box plots and dot plots. For a box plot, use the box plot function. That's easy. For a dot plot, use a strip chart function. So this is how we can use them. Okay. Let's see. Let's make sure I'm only doing one plot per graphic sheet. So box plot. And in our particular case, our data is arranged so that I have two columns of data in my data frame, and I want to have a box plot for both of them so I can make some direct comparisons. In fact, actually, as I said before, sometimes it's easier when you're introducing graphics in class, so you should look at the plot first. So this is the plot that I actually want. I have the two box plots. They're going up and down. You could do more of a horizontal version if you wanted to. Instead, I chose the default here. And I plot the dots on top of it to show what the actual data points are. Notice how those points are moved in an x-axis direction there. Does anyone remember what the name of that is in statistics? What do we call that? Yeah, I'm jittering the points to prevent overlapping of the actual points there. And so, we can see that roughly these points and these box plots have a very similar distribution. The only difference is the high school GPA can go a little bit higher than a 4.0, and that's just because of advanced placement. Advanced placement classes in high school that allow you to have a higher than a 4.0 GPA. Okay, let's talk about how to do the plot then. So the x argument is just GPA. And, this is optional. I decided to make them light blue. In terms of the fill of the box, I put a title on my plot, some labels. Here's an argument names that says, well, what do you want to be on the x-axis for the actual names of each plot? The default is just the variable names. I decided here to show you what it looked like if I specified names here, because I think they are actually a little bit better than what the variable names are. And then lastly, I have an argument here called parse. And parse takes on a list as the argument value. We've talked about lists before. If you remember with respect to estimating a regression model, VLM function, what's returned is what's called a list format. You can actually create your own list very easily. So for example, if I do list, we'll just call the first component X, and let's say, it's going to have a value of A, it's going to have a value of B, and then I'll have another component, we'll just call it Y, and it's only going to have a value of 1. And so that's an example of a list that I just created myself. Okay? Now, some arguments and functions require you to give the components in terms of a list, and parse is one. So I say list, and I'm only going to do one thing here. I'm going to change the out plotting character. What that means, and again, it's just a matter of looking at the documentation. If any points go above the fence or below the fence, what plotting character do I want to use? Well, I'm going to put an NA there, meaning I don't want any plotting character. Why? Because then I'm going to add a dot plot on top of it, and that's going to capture any plotting point that would actually be outside that fence, because it would be plotted as a dot, essentially. Otherwise, if I don't do that, you're going to see 2 points representing the same observation on a plot. Now, to do the dot plot, I'm going to use the function strip chart. And again, for the x argument, I can just put in my data frame. I decided to make the plotting points a little bit thicker than normal, so I said line width equal 2. The color of them red. Here's my jittering for a method. I want them the points to go up and down. The plotting character is just going to be an open circle, and then I need to add it to my current plot. Now remember that jittering there is done in a random manner. So if I were to run this code with box plot and strip chart, just those 2 functions, if I were to run that code twice, I would get a different looking plot because the points are randomly moved in the x-axis direction. So instead, so that I can always replicate exactly the same plot, I'm going to set a seed number. We've talked about random number generation before. Seed number allows you to always get the exact same random numbers back. Well, we can set a seed number here so that we get the same movement in the x-axis direction every time I run the plot. So to set a seed number, guess what? There's a function R called set.seed. And in parentheses, you put the seed number. It doesn't matter exactly what you put in there. I allow my fingers to randomly choose 7128. So when I execute this code, I get this nice little plot here. Same as in the notes. This is one of my more favorite plots by actually overlaying those dots on top of the box plot. Any questions? Okay. Let's see here. Now, sometimes your data, when you get it, is in a different format. Rather than plotting each column of the data frame as separate boxes, or separate box plots, or separate dot plots. Sometimes your data is structured like this, where you have a variable, and in this case I call it school, that's essentially classifying what the actual response variable is, in terms of classifying in terms of categories. So in this reformulated version of the GPA data, I have school, which lists, is it a high school or is it a college? And then I have a separate column which corresponds to the actual numerical response, the GPA. This is often a form of that you have for data. Now, when you have data in that format, you can't use box plot and strip chart exactly the same way. And so in this particular case, with box plot, I can use a formula argument just like what we saw with the LM function. I can say formula equal, what do I actually want to plot? What's the numerical variable? GPA. Tilde, how am I going to classify these GPAs? By school. I plug in, well, where is my data? Suppose my data is in hs.college. And then I could do a lot of the same options as before. And there's my box plot. Now, in terms of the strip chart, the syntax is just a little bit different. Surprisingly, there's not a formula argument. Instead, you still have to use the x argument. But otherwise, everything remains the same. Now let's talk about how I got the data in this format to begin with. So again, here's hs.college. This is the whole thing. How can I take my previous data frame and put it in this format? Now, would you want to do this in application? Typically not, because you could do the plots without doing this. But there are other situations outside of plotting where you need to know how to rearrange your data into the proper format to get some kind of function to work. And so this will be a nice illustration of how to do that. Okay, so this is on page 19. So the first thing I'm going to do is I'm going to create a new data frame that has only the high school GPAs in it. I'm going to call it hs.only. So it's going to get a data.frame, or I use data.frame, the function. And I'm going to create a variable called school, value hs. Then the GPA, I'm going to create a new variable called GPA. It has all the high school GPAs. Now remember, how many things are in this GPA.hs.GPA? There are 20 different numbers in there. Okay? And look at here, HS. That has only one value. So what I'm trying to, initially you might be thinking, okay, I'm asking R to put something that has only one value in a data frame with something that has 20 values. How can you do that? How can you put them together into a data frame? How can you concatenate, you could say, by column? Well, R does something what's called recycling. I don't think we've talked about recycling in the context of R in this class before, have we? I don't think so. Okay. So whenever R encounters a situation like this, R will say, okay, well, that school variable has a lot less values in it than the GPA variable. So in order to match everything up to be exactly the same length, HS is recycled 20 times. It's, in other words, repeated 20 times so that indeed you get a data frame where every variable has exactly the same number of values in it. So again, this is the name that R uses. It's called recycle. You'll see this in other places in R too. So I do a very similar thing for the college GPAs. And then I need to, now what I like to do is I have my, I'm going to put my high school GPAs up here in a new data frame. I'm going to put my college GPAs right below it in the same data frame. Since I use the exact same variable names, I can easily do that with the function called rbind. R stands for row. I'm going to combine by rows. So in SAS, the equivalent would be doing a data step where you would have, let me get my Windows journal out here, where maybe you have data set 3, and then you say set 1, set 2. That would be the equivalent. Okay? And so that when I do that, then I get, then again, the correct version of that data frame. Any questions? Okay. That takes us into about page 19, talking about the layout of plots. What I mean by that is similar to what we've seen before, where I can put multiple plots on the same graphics, let's call it sheet, or graphics window. I can put multiple plots in the same graphics window. And the mfrow command allows you to make frame by row. There's also mfcolumn command, which says make frame by column, which just puts the plots in a different order. It fills up the columns first before it would fill up the rows. Try it on your own to see how that works. And so now I want to talk about this some more, but also talk about some additional arguments or in part that are often useful when you're trying to get a publication quality plot out there. And so what I'm going to do, find the right part here. So what I would like to do is create the following plot. Simply, it's the box and dot plots again, but they're not on top of each other. Now, typically, I would always put them on top of each other, unless there was just so many observations that those dots basically hide the box. But I'm doing this more for illustrative purposes to help teach you some stuff about how to arrange plots properly. So I like to be able to produce this plot. Notice we have two separate plots. They have exactly the same y-axis, which of course would be needed because I would like to be able to make comparisons on the right side to the left side. So you need to guarantee that you have the same y-axis limits. Also notice that they share one plot title as well. Okay. So I'm going to use a par function to split up my graphics window into one row, two columns. And then I want to make sure again that I have the same y-axis limits. So I'm going to find the minimum of all my GPAs. I'm going to find the maximum of all my GPAs by using the min and the max functions. The reason why I want to do that is because then when I use the box plot function and the strip chart function, I use a y-lim argument that actually puts in the minimum and actually puts in the maximum. And again, this is an illustration of nice things that you can do in R. If I want to see what those minimum and maximums are, I can simply go into the box plot function, highlight that vector that's created by the C function, and run it. And I can see what the min and the max are. Okay? So, it's amazing. This only happens on kitchen spots. There we go. Yay. Okay, so now I got my box there. Ooh, notice I'm missing a label here. We'll talk about that shortly, why that can happen. So you don't see college GPA down there. Now, something that I wasn't trying to highlight, but I unfortunately did, notice I also have the title of the plot here. Now, I'll talk about that shortly, too. So let's go ahead and put on then oops. Oh, I cannot highlight the proper things. Let's try this again. Here we go. Okay, so now I got my plots. Notice the y-axes are exactly the same for the two. Let's first start talking about this down here. We have this missing college GPA. That will happen where R will omit an actual label when it feels as though it cannot fit in college GPA there without overlapping with something else on the plot, maybe another label. So what are fixes to it? Well, simply make the plot bigger. So I simply drag it over, and now it's there. So if I drag it back, you can see, oops, you can see what happens. So that's the simplest fix. There's also an argument that you can use with a particular, you can use with these functions, like box plot and strip chart, that makes the font size smaller for those labels. That argument, which is in the notes, is cex.axis. You can even rotate the axis labels as well. Unfortunately, off the top of my head, I don't remember what the particular argument is. But you can do that. And so you can rotate it so instead of it going across, you can make it go up and down. Or you can just slant it. And that can be helpful, too, to make sure you get all the labels in. Now let's talk about the title of this plot. So I didn't mention this before, but notice I did not include a main argument for either of these plots. And I could have. I'm going to go ahead and put the main argument in there. Let's go ahead and run it to see what it looks like. Of course, I didn't do it right. And so you could have separate titles for both, and that would work in this situation. But there are times where you would like to actually share a title between two plots that are in the same graphics window. And the way to do that is actually with a little trick, you could say. There's actually a function in R called title. that allows you to put titles on plots, individual plots. But the trick comes in, and notice how the argument's made, just like what we've been using before with some of these other plots. The trick, though, is to say to R, draw this title outside of the main plot that was just drawn. So here I have my box plot, and then when I execute this, draw the title outside the main plot and allow yourself to use the entire graphic sheet. That's the trick. Line equal -3, go down from the top 3 lines. And that's where you draw the actual title. So if I run this code, I'll go ahead and just simply leave the main from the box plot and dot plot in there just to show you what it looks like. You can see how that was drawn. You're going to try line equal -1 so you can see what the result is. By changing options like this is how you learn how to program properly in R or in other languages too. Are there any questions? Okay, let's go further with these plots. Now, if you notice, again, they share the same y-axis range. Do I need the y-axis labels for the second plot, the dot plot? Well, no, I can get it essentially just from the box plot. And it might be nice, too, if maybe I could, let's say, move the 2 plots closer together so that you can see it better that they're basically sharing the same y-axis. So let's talk about how I can move them better together, or closer together. And what I want to do is produce this plot here. Notice how also I'm going to put the y-axis label on the strip chart. I'm going to put it on the right side as well. Okay. So let's talk about how we can do this. Again, the power function has many different graphics parameters that control how a plot is actually being made. And there is a argument called mar for margins. In order to draw these 2 plots closer together, I want to make the margins for each of the separate plots smaller. And so if you look up the help for par and go down to where you see MAI and MAR, you can see essentially that margin 1 is going to be the bottom of the plot. Basically the distance between that square that contains the plotting points and the bottom of the graphics window. Margin 2 is on the left side. Margin 3 is on the top. Margin 4 is actually on the right side there. You can kind of see this page up by how this is in a particular order. And so mar itself gets a vector of values where you say, how big do you want your bottom to be? How big do you want your left side to be? And so on. And this is an error in the notes. The units that these are being measured in is not inches, but lines, relative to whatever font size you're using. So if I say 5, which is the default for the bottom margin, that's 5 lines, not 5 inches. So the default is 5, 4, 4, 2. And so for my box plot, in order to remove part of that right margin, I'm going to reduce that from 2 to 0.5. For my dot plot, I'm going to reduce the left margin from 4 to 0.5 to put and to remove the y-axis on the dot plot. I say y-a-x-t equal quote and end quote. We've seen that actually before in the Intro to R notes, or y-axis title, essentially. I think that's what the T would stand for, or tick marks. That would probably be a better way to put it. Y-axis tick marks, no, don't put them on there. But I would like to have the tick marks on the far right side. So how do I do that? Remember seeing the axis function before? I say axis. Where do I want to draw some tick marks? I want it on side equal 4. If you look up in the help, side equal 4 is exactly the right side of your y-axis. And here I get my plot. Okay. Yes?
That axis just goes to whatever you plotted last?
Yes, exactly. So it goes to whatever was plotted last. And that's an important thing. So there are, and I forget the exact terminology in our, I apologize, but there are these main functions that create stuff. And there are other graphics functions that add stuff. Strip chart actually draws a plot. Axis just adds to the current plot. Now, we're kind of talking about some of the finer points of plotting here. Maybe it might be boring, but I think of, you've heard the phrase, a picture is 1,000 words, or means 1,000 words, or whatever. Getting a plot in its best format possible can be so helpful when you're trying to explain something to somebody else, or just for yourself to understand what something is saying. And I sometimes will take hours getting a plot in its exact form that really tells the whole story. And so by knowing these little options that essentially we were talking about, that will get you started towards in the right path of not just going with the defaults. Try to make your plot look cool. Let it tell the story properly. And hopefully this will get you on the way of doing that. Are there any other questions?
Why in the figure the x-axis between two tick marks is darker than?
Yeah, I didn't notice that until later after I made my notes, and I don't know why, to be honest. And I find that annoying, to be honest. There are ways that I have not tried it with strip chart, but there are ways that you can somewhat control that. I think maybe why I haven't paid much attention to that is because normally, this plot, I always draw it on top of that plot. And so when you do that, I don't think you notice you don't have that. Let's actually look at one of the previous plots. No, you don't, which is odd. Why not? Why isn't it there? I would imagine, and you can even notice this on the right here too. You lose that. And I bet what you could do is, if you notice in this plot here, when I did the axis function, we no longer have that. And so I bet you could probably manually draw in that x-axis and get it removed. And again, these are things that you would want to consider when you're trying to get a publication quality plot. So if you're interested in, actually publishing something in a journal, you want to get that plot exactly the way that you want it to, so it looks good, because other people are going to be looking at that. And those are kinds of things that you would probably want to try to fix. Other questions? Yes?
Can we change both the axes at once?
When you mean both the axes, which axes are you talking about?
Like, so you took the y to the right side.
Yes.
So like that, can we take x to the top?
You can take x to the top. You would have to use two different axis function calls. And the reason is because, you have to say, well, what are you dealing with? And you can only do one at a time. I'm 95% confident you would only be able to do one at a time. You could try it on your own to see if you could do two at a time, but I think that might be actually confusing.
So we do one and then again do the other?
Yeah. And the only thing I'm thinking of is maybe you could do this. I don't remember what the bottom number is for the axis. Maybe you could do something like that. I'm not for sure. Other questions? Okay, so there are other ways that you can arrange or even have greater control over arranging plots in a graphics window using the graphics package. And that's through using the layout function. You're not responsible for it. I rarely use layout. I have used it some, but rarely, and it's come in handy when I've used it. But I decided just to save time and to not go over it. So you're not responsible for it. You're welcome to take a look at the notes, of course, and you can see if I come down here. So, for example, you can divide your plotting window into 3 parts, where it's not necessarily, like in a matrix structure like MF row would allow you to do, but you can, really arrange stuff however you want it. And so, for example, at the very end, I show, well, suppose you did a scatter plot and you wanted to add box plots to give a one-dimensional summary of each variable. And lastly, on page 27, I go over the ggplot2 package. As I mentioned at the beginning of this section, we're going to skip that. If we have time, I will come back to it at the end of the semester. It's just another way to approach graphics in R that's quite popular. Okay. Are there any questions? Okay, let's move on to the next set of notes then. We're going to talk about how we can use LIX and R together so that you have your LIX document and you type up the document just how you would normally, but now you're going to actually insert the R code for whatever application that you're interested in. And then when you hit the compile button in LIX that creates the PDF, not only is MikTeX going to run and create the PDF, but also R will run at the same time and put in the R code and output into the document itself. Why would you want to do this? Well, one of the big reasons is due to the concept of reproducibility of research. Let's say you're writing a paper for a journal and you have a statistical analysis section in that paper. Well, wouldn't it be nice if the document that you're actually typing up, the paper that you're talking about typing up, actually includes the corresponding analysis code right in there, and also the corresponding output that you use to analyze, whatever you're analyzing. So obviously, in that setting, it would be helpful, but even the reproducibility of homework. For any class that you do where you're allowed to use R, oftentimes you're typically writing up a report and you can include all your R code and your output all in there at once. This also helps prevent copy and pasting errors. Very often, when you're doing an analysis for a class or obviously for a journal paper itself, you're having to run the code multiple times. And what if you forgot to copy over the latest run of the code that you're actually wanting to use to analyze? That happens. And so by essentially knitting the code and the output and the regular text together, you're not going to have those kinds of issues. I won't get into that example. So to combine LIX with R, we use an R package called knitr. It's not knitr. I originally, when I first saw it, I always thought it was knitr, and I actually always pronounced it that way, but it's actually called knitr. Well, where does the name come from? Well, if you remember just a few minutes ago, I used the word knit. I am basically knitting my R stuff together with my LIX stuff. And you can even use this with LaTeX too. I'm putting them together in the same document. The author of this package there, his name is, I hope I pronounced this right, Iwei Shi, and he's the one who wrote this book here that's a recommended book for our course. So this is a whole book on this package. 250-some pages. Interestingly, he wrote the package. It's only been around for about 5 or so years, and this was one big component of his dissertation that he did in the Department of Statistics at Iowa State. His whole dissertation was on, I think it was basically 3 packages that he wrote, where this was the main one, and he turned this main one into a book. It's actually in his 2nd edition. And also interesting, she actually, I think, lives in Omaha. He works for our studio. He's probably one of the most well-known people in R right now. He works for our studio, but he works from Omaha to do that. And I think our studios, their main headquarters, I think, is based in Texas, I think. I could be wrong. And he actually came and gave a seminar in our department last spring. He is somewhat, this is just my opinion, he is somewhat opinionated on what's the best way to do stuff. And I think you'll see what I mean when we take a look at some of the stuff that he did for this. So the knitr package can be used with LIX, can be used with LaTeX to merge R code and output in your PDF with regular old text. There's another way to do some of this stuff too, and that's to use something called Sweave. So look at the name S-Weave. The origin of R comes from the S language, and you're essentially weaving together R stuff with regular old LaTeX. And so that is another way to do it. And this is older. It's been around maybe 10 years or so, but it's not as user-friendly. So we won't talk about that. I think most people have migrated over to the knitr package. Okay, so how do you get LIX ready to go? How do you get R ready to go to do something like this? First thing you need to do is install the knitr package. We've talked about installing packages before, so install it. Again, if I were to do in my R console here, packages, install packages, find a local source to install it from, and you just page down to wherever you see the knitr package. Oh, it's always difficult. There we go, right there. And click OK, downloads it, installs it. Okay, so once you got that done, then you got to do some stuff in LIX. Okay. It's a little bit more difficult than what it should be, to be honest. For some reason, some of my settings here are kind of screwed up, but you can still see document here. So document, settings, and if I come up here to modules, I can't make it any bigger, so I'm sorry, but if you come up here to modules, what you're going to see are what are available are a number of add-ins to LIX to do things that you normally wouldn't be able to do with LIX. And you're going to see one called RNW, and in parentheses, knitr. Okay? You click on, I've already added it in, but if normally this button will be available, I click on Add, and then it will come over here as selected. When you click on then OK, you've done one step of making the knitr package available to you. The next step. Make sure I do talk about everything here so I don't forget something. The next step is that you need to tell LIX, where is R on your computer? So I can come up here to Tools, Preferences, and Paths. So paths basically means is like where does R put, see this temporary file, temporary directory there? Whenever you compile a PDF, if you remember, it doesn't actually go to the actual folder where your LIX file is. Unlike with LaTeX, if you were to compile it, it would actually go to the folder where you're working in. Instead, whenever you create a PDF using LIX, that PDF actually goes into that temporary folder right there. Now, what we're interested in, though, is this right here, path prefix. And I know it's extremely small, but I do have it in the notes. And this is where LIX looks for external software. So, for example, I know it's hard to see, but there's a reference to the location of Python. There's a reference to the location of Perl. LIX uses these for its actual program to get everything working. And so, at the very end, maybe I could just go over here. This will be bigger. Yeah. So at the very end, you need to actually type in the location of R on your computer. This is the location of R on my computer when I'm using R 3.2.2. Now, how do you know exactly where it's located on your computer? Well, obviously I have a Windows computer here, so that's the only way I'm going to be able to demonstrate it. But if I go under just my C drive, if I come over here to Program Files, R, and right now I'm just using 3.2.2. Now, R puts the executable R file, so the actual file that you could click on to open up R, under bin, and if you use 32-bit, i386, if you use 64-bit, which is what's shown in the notes, x64, and now you see a bunch of executable files. So for example, if I were to click on rgui.exe, that should look familiar. And there's many different ways to run R. We've already done the R GUI, and then we also did just the plain old R console. What knitr uses with LIX is this way called rscript.exe. I don't think it's really important for us to get into exactly what rscript does. If you want to know more, I give a little bit of information in the notes. And also in my Stat 950 Computational Statistics 1 class, I actually also go into some detail about what rscript does in a high-performance computing context. So, what we basically need to do is this. You need to copy and paste that folder, that entire directory, right at the end of the path prefix that's already there. And notice I separate the previous one that was there. So there's a number of prefixes. They all are separated by semicolons. So you put a semicolon at the end of the very last one, no space, and then the actual folder on your computer where R can be found. Okay, we're almost done. So obviously click on Save, click on Apply. Next, click on Tools, Reconfigure. Basically now you need to tell LIX, hey, I got this new set of preferences. Go find it. I don't know why you have to do that, but you do. So you say Tools, Reconfigure. And then one last step, you have to actually close out LIX and then reopen it. And then you're set to go. Yes, it could be easier. But again, how much money are we paying for this? $0. So just remember that. These are the steps, though. Okay. So, at least we're out of time with respect. Yes.
And that'll be set for as long as I
Yes.
LIX.
Thank you. Yeah. If you download a new version of LIX, you would have to go through the same steps again. Okay. We're going to talk about the assignment next, but for all future work essentially in this class, you need to use knitr and LIX. Obviously, we'll be going over that over the next few class periods, exactly how to do that. And all my lecture notes for the R portion of our course are done using knitr and LIX. And basically what we're going to do is that we're going to use those ERTs, those evil red text boxes, and we're going to put our code for R inside of there. And everything's nice and merged together. Okay, let's talk about the assignments. Okay, so this is assignment number 6. So, similar format as before. You can work in pairs. What you're going to be turning in this time will be your LIX document that uses knitr to use R. And you'll be turning in the PDF. Just 2 things, that's it. That's the only things that you need to turn in. You won't have to turn in any kind of images, separate like image files. You won't need to do that because essentially everything will be inside LIX already. Problem number 1. Go away. There. Problem number 1. Continuation of problem number 1 from assignment number 1. And you're going to do some stuff that you've essentially already done in SAS, but now you're going to do it with R. Again, I think it's just a great way to learn the 2 software packages to do that. So problem A, and again, this is with the NFL Combine data. Construct side-by-side box plots of the 40-yard dash times for each position. Change some of the defaults, such as I want a yellow fill for the box. It just shows me that you understand how to do that. Part B, side-by-side dot plots. So when I say side-by-side, if you remember there are, I think, 7 different positions. So you'll have a separate box plot for every position. You'll have a separate dot plot for every position as well. Then part C, combine the plots together in a 1x2 grid. So just like what we did with the box plots for the high school and college GPA data. We have high school and college GPA box plots here. We have the dot plots over here. Now you're going to be doing it for these, for the NFL Combine data. Part D, overlay the plots onto one plot. So you're going to be doing a lot of the same plots. You're just rearranging them. And it just gets you experience similar to a lot of the stuff that we did today. I don't think that this will be difficult. Part E. Now you'll notice that the boxes and also the dot plots are ordered by DB, LB. In other words, it's alphabetical order. I want you to tell me why that occurs. And again, it just comes down to understanding how R deals with factors. Remember, factors are essentially qualitative variables in R. And we've talked about this, not in the last sentence, not in the graphics notes, but in the previous notes. Part F. Construct a scatter plot now, 40-yard dash times versus bench press weight. In your plot, include the following. I want you to vary the plotting symbols by the actual position. Add grid lines to the plot. Make sure you change the X and Y axis labels from the default. And also put the name of the player with the largest bench press value. Put that name of that player right next to the actual plotting point for that. And you've done that in SAS, well, do it in R. What function do you think will be helpful for that? Does anyone remember? Okay, you'll figure it out. Part G. Construct a function now that produces a scatter plot like in part 1F, again, but can be used for any 2 numerical variables in the data set. Remember writing a macro? Well, now you're basically now doing the equivalent in R with writing a function to do this. And I give you some guidelines corresponding to, well, what this function should do, how it should work. Run it with not just the 40-yard dash times and bench press, run it also with height versus weight to show me that indeed that this function is written general enough that it can be used with 2 other variables too, without changing anything inside the function itself. Any questions about number 1? Okay. Problem number 2. Continuation of problem number 2 from assignment number 1. Well, we were doing that in assignment number 5 as well. And if you remember, you got to this point here. We had time, potency. You had a scatter plot of your data, estimated regression model. You had the confidence interval bands. You've already gotten to that point. Now what I want you to do is add some stuff to that plot. Add a legend that tells me what those lines are. Also, this then gets into finding that shelf life or the expiration date. I want you to actually draw on the plot, something that looks like this, where it intersects that 95% lower bound. So this is at 0.95. And then it comes back down, and there is that shelf life right there. I want you to actually draw that on the plot. Part B, find the shelf life using a grid search in R, similar to what was done in assignment number 3. That was done with SAS. Note that a loop is not needed to solve this problem, unlike what I did in my answer key for assignment number 3. If I see a loop, I will deduct points. No loop is needed, and that's just because of how R performs its calculations differently from how SAS does. You can work with vectors a lot easier. And lastly, part C, find the shelf life with the help of the uniroot function. Okay. Remember, so here's assignment number 3 again. Remember, all you're doing is finding a root to this equation there. Okay? In R, there is a nice little function called uniroot, where all you have to do is write a function. Let's call it myfunc, for the lack of a better name. That maybe has a value of x, or an argument of x. And inside the function itself, you can do this essentially in one line. You basically write out part of that equation. Not that part right there, but write out that equation. And there's your function. Let uniroot call that. And you tell uniroot, hey, look between, let's say, a time of 0 to 60 and find the root of the equation. Solve for x. Now, obviously, we haven't talked about uniroot in this class. But again, outside of this class, you're going to be faced with many situations where you find a function that's going to do what you need done, and you're not familiar with it. And you have to figure out how to use it through reading the help, looking at the corresponding examples, maybe doing some Google searches to see how other people have used it in the past. In the end, uniroot is not very difficult to use, and it's a very useful function. So I want you to use uniroot, that function, to solve this problem. Any questions? Okay, problem number 3. Continuation of problem number 3 from assignment number 2. In that particular problem, you were finding a t-distribution table. Okay? Do the same thing in R. And again, no loops are needed to do this, due to how R actually does its calculations based upon vectors. If I see a loop, I will deduct points. But construct the t-table, nicely organize it, similar to like what we had in SAS. Lastly, problem number 4. Let's say that Z has a standard normal distribution to it. Complete the following using R. Part A, well, simply find that probability. Does anyone remember what the function's name would be? The word norm, what? Norm will be part of it. P-norm, yeah, probability, normal distribution. In any kind of probability distribution function, P corresponds to probability. Q norm, Q for quantile. D norm stands for density for that distribution. R norm stands for randomly generate numbers from that distribution. Okay. Plot the probability density function. So plot a standard normal. I think we even did that in class once already. But what we haven't done in class is I want you to actually then shade. you often see this in applications. So here's my normal distribution, kind of. Here's 1.96. I want to see that area underneath that curve. In other words, that probability. I want to see it nicely shaded. Not like that. That's not nicely shaded. But I want to see it nicely shaded. And again, this is another example of, okay, well, how do you do this? Originally, when I was going to assign this problem, I wasn't going to tell you what function to look at. Because, again, to emulate a situation that you will have outside this class, where you might have to do a Google search and figure out, well, what function is going to allow me to basically to color that in. I decided to help you out. Maybe there's other functions that will help you do this, but this is the one I use in the answer key called polygon. And I did a simple Google search, and I found a nice, useful blog post of how to do it. Part D, well, you've plotted the PDF. We've actually done that in class, I think. Well, now plot the CDF. Plot the cumulative distribution function, and do that same kind of shading as well on the CDF plot. Okay. So, that's assignment number 6. Are there any questions? I think this will give you some good experience of working with R. Okay. If there's no questions, then that's it for today.